Hello and welcome to Group 6's video on how differential equations can be used in mechanical engineering, specifically in the analysis of mass spring systems. To solve differential equations, first the equation has to be classified. Start by identifying the dependent and independent variables. The independent variable will be the denominator of the derivative. Next, classify order and degree. Order is the highest derivative term in the equation. Degree is the power to which the highest derivative is raised to. Following this, determine whether the equation is linear. A linear DE is where the dependent variable and its derivative are first degree and there are no products involved with the dependent variable or its derivative.
From the previous slide, to classify this example, we know that it's a second order differential equation to the first degree and is linear with constant coefficients.
We can see that this differential equation is homogeneous because the right-hand side is equal to 0. In order to solve this differential equation, we must substitute y equals e to the power of kx into the dE. From this, we obtain k squared plus k minus 6 equals 0. We solve this to find k equals minus 3 and 2. We substitute this into the general solution from the previous slide, obtaining a complementary solution of a e to the minus 3x plus b e to the 2x, where a and b are arbitrary constants.
When solving the quadratic equation for k, if the discriminant is greater than 0, then the general complementary solution becomes yc is equal to a e to the alpha x plus b e to the beta x. And if the discriminant is less than 0, then yc is equal to e to the alpha x bracket a cos beta x plus b sine beta x, close brackets. And if the discriminant is equal to 0, then yc is equal to brackets a plus bx bracket e to the alpha x.
Second order differential equations have a variety of applications in engineering, but in this video we will see how they can be used to analyse the mechanism of a mass spring system. Second order differential equations can be used to find the length of the oscillating spring at a certain time, and can then be used to find the tension in the spring and the forces acting upon the attached mass. Furthermore, they can be used to analyse the motion of the mass that is attached. The two figures on the left of the screen show a mass connected to a fixed spring of certain length at the equilibrium position and an extension length x. Figure 1 is a vertical spring system, Figure 2 is a horizontal spring system that has been stretched, and Figure 3 shows the forces acting on such a system. According to Hooke's law, the restoring force is equal to negative kx, where k is a positive constant known as the spring constant. By considering Newton's second law of motion, force equals mass times acceleration, and by assuming that there are no external resistive forces acting on the system, such as air resistance or friction, we can equate mass times acceleration to negative kx. According to basic kinematics, if position x is a function of time, then acceleration will be the second derivative of x. Therefore, mass times acceleration equals negative kx becomes a second order homogeneous linear differential equation with constant coefficients, where m is multiplied by the second derivative of x added with kx. This equation is equal to 0. The differential equation yields the auxiliary equation shown. Solving this equation gives r equals plus or minus the square root of k on m multiplied by I. W can be substituted in to simplify the equation. The general solution of the differential equation is as shown. The following example shows the real-life application of differential equations. Conditions are given as per the scenario and an equation must be found that describes the motion of the mass. By using Hooke's law and substituting in values as given into equation 1 from the previous slide, we can determine a general equation with arbitrary constants. By then using the initial conditions, we can solve this general equation to find out what the constants are and hence find the true solution.